Started. Apologies for the chaotic start, but we're figuring out. Okay, so first of all, can you hear me or no? Okay, people in the back don't hear. So I can shout, or did you have a mic as well for this room? Okay, so I guess for now I'll just speak louder. Is that okay? Is the level here appropriate? Sorry for the people right in front. Okay, so the plan this afternoon is for me to introduce you to the toy code that we're going to be using. It is, well, I guess it depends on your perspective. If you're more used to commercial software, it will be a long and complex code. If you're more used to you're developing your own computational tool, it will be more of a toy software. It's a few hundred lines. It's, I think, reasonably easily digestible. It's all written in Fortran 90. So hopefully you're all reasonably familiar with it. If you're not, the language is not that different from what you would get in from, say, a standard MATLAB type language. So in my mind, it's reasonably easy to pick up. But I'm biased. I've been using this for a while. Let me think a bit. I said Fortran 90. It's not quite true. There's a few things that are in Fortran 2003 and 2008. So before we start playing with that, and since it seems that we also need a bit of time to make sure that everyone has their login and everyone has access to their computer, what we're going to do is talk about the underlying method at the basis of the code that we'll be using, some of the underlying assumptions, and then what we'll do after we've talked about this is we'll just use this code as a kind of a black box a little bit. I'll walk you all through each of the routines. There's not many of them. Today we'll stick to purely single phase flows. We're not going to look at anything particle related or interface related. This will start tomorrow. Okay, so today I'll have you compute a simple Poiseuille flow. I'll have you compute a von Karman vortex street behind a cylinder. In fact, I need to. I've done that a little while ago. I'm not sure if it's a cylinder or a square. I don't remember, but we'll look at what's in the documents. So let me start with some of the basic assumptions that we'll make. One assumption I mentioned already. It's the fact that we're going to assume a constant density. There is nothing regarding the method that requires that at all. It is just purely a convenience-based assumption. It allows me to cut down the size of the code, and it allows for faster development, and we're going to be able to do things more quickly together. The second assumption, which is a pretty obvious one, is that we're going to stick to 2 dimensions. The reason for that is because those computers are what you're using. Okay, so that you don't have supercomputing resources available right here for this exercise. And so we'll have to limit ourselves to what's available. This is a pretty major change. If you wanted to take that code and make it a reasonable tool for engineering purposes, you would want to go 3D, you would want to go parallel, you would want to do a number of things that would make this code increase in size and complexity enormously. So it's also a choice of convenience. I mentioned that, or I guess I hinted to that already. This code is a serial code. There is there is no OpenMP, no MPI, no parallelization whatsoever. If you wanted to do that, it would be a pretty serious time involvement, not necessarily a very complicated task, but a lot of the routines would have to be restructured in one way or another. This is not the topic of this course. We're going to try to talk about the detailed methods, so we're going to leave that behind. As a result, what we're going to be able to look at will be limited by what your machines here can do. I have no idea what those machines can do. I've assumed that they would probably be more powerful than my laptop. I don't know. We'll see. Chantal, do you know how how old those computers are, or how recent they are? Or
Okay, so they are in the down show.
they are, sorry?
HPC?
No, no, I'm talking about those machines here.
Yeah, these are Linux.
Okay, but what processor behind?
Oh, what processor? Maybe the very.
If someone is logged in, if you can do a quick check of what's
i7.
i7. All right, that starts well. Do we have a clock speed? Anyone with a clock speed? Say it again? 2.3. Okay, so that's about on par with what I have on my laptop, I think. Probably even a bit faster. So I think we should be good. There should be no concern there whatsoever. All right. Everything I've done, as I said, is in Fortran. We're going to use an open source software for compilation, which is the GNU Fortran, so G-Fortran. We're going to stick to that. It works really well. It's not necessarily the most optimal in a number of circumstances, but it's extremely serviceable. And that's what I'm using on my laptop as well. Let me see what else. Oh, so I've hinted to that already. We're going to forego any consideration of compressibility, okay? And so we're going to do that by using what's called a fractional step method. I'm sure some of you know what that is. I'm sure some of you do not. We'll discuss about that in the next, I guess, in the next 40 minutes or so. And I'll tell you exactly what is the underlying methodology that makes this flow solver work. So, incompressible, single phase for now, 2D, serial, constant density. Okay, so that's a whole lot of assumptions. This will allow us to compress this code into something pretty simple. There's a few additional things I've done. Any normal code will require restart capabilities. You would want to be able to stop the simulation and restart it at some later time. I did none of that. Okay, so this is the code that starts from some initial conditions with some hard-coded boundary conditions, and it runs until you tell it to stop. If you haven't told it to stop when you actually needed it to stop, tough luck, you'll have to restart. It's just basic, it's more work that's required if you want to add this capability. I thought this was not a particularly relevant thing for us to focus on, so I didn't include any of that. As a PhD student and as I kept going as a researcher, I've become more and more I've become more and more attached to the importance of visualizing what you're computing. I think it is very bad practice to have many steps between the computing process and the visualization and the internalization of what the results are. If many steps are required to process what you've computed and turn it into something that you can visually, intuitively understand, you're going to make a lot of useless calculations. So what I've always done in my codes is I've always worked hard to make sure that as I compute, I can visualize directly what's going on. So all this I've done here with one big assumption, which is that I've picked a single I/O format. Okay, so I've identified a format that I thought was practical for our purpose, and that's the only thing that the code does. It doesn't generate results in any meaningful way except spewing out visualization files, really, in a format that I've chosen. The format that I've chosen is called Nsight Gold. Nsight, I don't know if any of you here know about the Nsight software. It is a fairly common and very high quality scientific visualization tool, like probably the most well-known would be TechPlot, I would think. So it's similar to TechPlot. I think it is significantly more intuitive. It scales to enormous simulations. So that's something that I consider to be very useful in my day-to-day work. It's not going to be readily useful for us right here, because we'll do fairly small simulations. But I think it's a very powerful software, and I thought this is a good place to start. There's other advantages that have led me to choose this, which one of them being that the Nsight Gold format is compatible also with the software called ParaView. ParaView is an open source visualization software that has very similar capabilities to Nsight. So Nsight is a software that you have to pay for. ParaView. You can download it for free from their website. It's put together by a consortium of a number of people, including, I think, Lawrence Livermore National Lab, I believe, or Los Alamos National Lab. So you can do quite a bit of visualization with just the format that I've given you. The other reason that is even more pragmatic is that I know Nsight pretty well, and so I'm pretty comfortable with it, so I won't waste any time with it. The price of 30 Nsight licenses would be high, so what we're going to use instead is the free version. So if you boot up Nsight without a license installed, what Nsight will do, first of all, it will try to reach a license for maybe a minute or so. But then it'll say, OK, I haven't found a license. What should I do? And it lets you do a number of things. But one of the things it lets you do is choose to use the Nsight free version. This free version is limited in terms of the problem size that can be visualized. OK? We're running into the small problems. It's going to be perfect for us. Okay, there's no other limitation that I know of, at least. So I'm not trying to advertise for Nsight. A lot of other softwares are doing a very good job, but I thought this was a reasonable compromise. I'll tell you right away, I've cheated a bit. So if you have a purely 2D problem, Nsight limits you to visualizing like 20,000 elements or something like this, so fairly small grids. If you go to 3D, it lets you visualize a few 100,000 elements, so significantly larger grids. So the code is running 2D, the output is going to be 3D, a single layer of cells. Okay, so I just tricked the Nsight check for that. So I'll tell you where it's done in the code. This way everything will be clear and you'll know what's going on. Okay, so this is the overall idea of what we're going to be using. We'll start now by discussing about fractional step. Just to be sure, to get an idea, who here knows already about fractional step methods? All right, so I'm sorry for the couple of you who know about that. So we'll use that we have to solve simultaneously for velocity and pressure, okay? In the context of a purely incompressible problem, there's a number of things that can be used to do the simultaneous solution of velocity and pressure. And so we'll talk about one of those solutions. Okay, so one thing we need to figure out is how large I need to write for you to be able to read here. So let me start just by writing the equation. You'll tell me if you can read. Is that too thin? Is that readable for everyone or not? Okay. So I usually write smaller than this, and so I'll probably slowly shrink over time. At some point, you'll tell me, hey, it's becoming impossible for me to read. Okay, so this is a conservation of mass. We're back to single phase just for the rest of the day. And then we'll include channels plus divergence of gradient of velocity, so the Laplacian of the velocity. Okay, so this is what we're going to solve. I'm making my life very easy here by saying rho is equal to 1, and this is a weird row. Let me rewrite this row. And I'm not worrying about any of that. Okay, so this is the problem we're going to be dealing with, and we're going to put together a scheme that allows us to solve simultaneously for U and P. The issue, again, the underlying issue here is that the continuity equation is related to the velocity, is related to the pressure through the momentum equation, also, let me know if I'm not loud enough. I will probably be slowly talking more and more quiet. It's okay? All right. And so then the connection between density and pressure happens through the equation of state. That's the simple, straightforward beautiful world of compressible fluid mechanics. This is not what we're going to be looking for altogether. So we're going to need some way that doesn't introduce equation of state and doesn't require a p-rho coupling to introduce an appropriate handling of the pu coupling. So let's talk about the handling of So, like I said, we're going to use a fractional step method with what's called pressure projection. The first discussion of this that I know of is by Chorin in 1965. So it's not a particularly new in CFD since the 80s, and it's remained very much relevant to incompressible CFD. It is tricky in a number of ways and very practical in a number of others. Okay, so first of all, let's talk about what it means for us to say that our density is constant. So what is the meaning of rho is equal to a constant? If we were compressible, we would expect that the change in pressure would imply a change in density related with the speed of sound a, such that a squared is just dp d rho at constant entropy. This should be nothing new. We're not going to talk much about this. But now we're assuming an incompressible flow. So if we're incompressible, can only density change the speed is infinity. Flow solver will be specific the speed of sound to be infinite. So now let's actually do the pressure. So if I want an equation for P, the simplest way I can do that is to take the divergence of Navier-Stokes. So the divergence plus divergence of u dyadic u of grad P nothing particularly exciting so far, except remember we're assuming that the divergence is 0. I can obviously swap the order of these two operators, divergence and d over dt. Therefore, I have the time derivative of the divergence of u, which is the time derivative goes away. So what we get from that is an interesting equation that tells us that the divergence of P is to minus divergence So that equation for one reason it has because it has no time dependence, it means that the pressure inherently in an incompressible flow has to adjust infinitely fast to any change of the velocity field. So if I change my velocity field through the solution of Navier-Stokes, it is reasonable to have a method that right away readjusts the pressure distribution in accordance with that equation. Okay? So we're going to design a method that does that. So here, again, the idea is P adjusts instantaneously. And to what? Well, to changes in so from this observation, we get to Chorin's idea. Chorin's idea was use of this change of velocity leading to a change of pressure to propose a two-step algorithm. The two-step algorithm is as follows. Step one, we solve everything without, well, plus 1 over the Reynolds number times the Laplacian of the velocity. So I have everything of Navier-Stokes here except for the pressure. This is obviously not Navier-Stokes. At the end of step 1, what I have is not a fluid, an appropriate fluid equation, or fluid solution. But then I'll add dt is equal to minus gradient of pressure. And so this implementation will take the form of, like I said, two steps. We'll first go from the velocity at time to the velocity that is, well, that's an ugly star. Sorry, I'll try a better star. There you go. To u star, which is the first guess of the velocity at n plus 1, but it's an incorrect guess. We don't have the action of pressure here. And then step 2, we'll take this incorrect guess and add back what's missing to truly take us to the new time n plus 1. Now, specifically, we're going to think about a solution that is a viable solution that obeys both continuity and the momentum equation, because it misses, again, the pressure. So it's not obtained from solving the right equation. But we're going to say that essentially the second step looks a lot like a projection step. And if it can be formulated as a true projection step, then it can directly bring us back into the subset of solutions that are both in accordance with the continuity equation and the momentum equation. As standpoint, we catch here the vector fields u of x. Okay. We start initially we are in, oh, I'm sorry, I'm missing one thing. And then we're a sub-potato there. That sub-potato is going to represent of all solenoidal. U such that the divergence of U. Okay, so we have two spaces, all the possible solutions that, say, our mesh can support, and all the possible solutions that our mesh can support, but that are also divergence-free, solenoidal. Okay? what we're going to do is we're going to assume that we're starting at time n from, say, a blue solution here, and that that solution lives in the space that contains that space of divergence-free solutions. So that's going to be, well, that blue looks like black. Let me redo this. That's good. So that's going to be my U at n. It is within my red space. It's an acceptable solution that verifies both continuity and. Now, step one of Chorin's algorithm is going to take us from UN to a U star that is unspecified but has no guarantee to live in that subspace of solenoidal velocity. So we're going to end up, say, right here. So that's going to be step one of Chorin's algorithm. It's going to take us to U star. This U star is not acceptable. We're going to use step two to project this velocity field back to the subspace fields. To be giving us our UN plus 1. Okay? So, UN is solenoidal, UN plus 1 should be, U star is not. So, any questions so far on this? This makes sense? Okay, so let's talk about how we're going to do this concretely. So the simplest approach that can be conceived to take us from there back to there is to do a pure geometric projection. Literally, we're going to project onto the subspace that has this characteristic. What does a projection mean? Well, a projection means that we're going to look at divergence, the solenoidal part of the velocity, and we're going to explicitly remove it. So let's look at what this means. Step. By enforcing divergence of the velocity is equal to 0. Specifically, this constraint is going to be what's going to lead to step 2. Okay. Well, to figure it out, we're going to go back to this notation where I use an n, a star, and an n plus 1. And I'm going to semi-discretize step 2. I'm going to discretize in time, not in space for now. So discretization in time. So semi-discretize step 2. And it's going to need to be equal to minus grad p. Right? If I scroll back up, this is my step 2 here. du dt is equal to minus grad p. So this is what we're going to do. If I'm properly semi-discretizing, so if I'm discretizing in time, I need to assign a timestamp for my grad p. It really doesn't matter what it is. Ultimately, it doesn't really factor into the discussion. For the sake of simplicity, we'll say it's an n plus 1, but don't worry about this. Now we're going to take the divergence of that equation. That's going to give me that 1 over delta t times the divergence of un plus 1 minus the divergence of u star is equal to minus the divergence of the gradient of p at n plus 1. All right. Now remember, we want the divergence of un plus 1 to be 0. So we'll explicitly set this to 0. What does it give us? Well, essentially it gives us the end of the story, which is the resulting equation for pressure that we're going to be solving. We're going to simply states that the of the pressure at n plus 1 is equal to 1 over delta t times the divergence of this intermediate velocity field u star. So we took a first step that took us out of the subset of divergence-free velocity fields. We get this u star. It has a non-zero divergence. We want to get rid of it. Well, if I use this equation to go from u star to un plus 1, then the only clean mathematical projection that would guarantee that un plus 1 is divergence-free would be if I make sure that my pressure that I use here is such that its Laplacian is equal to 1 over delta t times divergence of u star. That's simple. So now I need to solve for p based on this right-hand side. So I have here a purely elliptic problem to solve. That's going to be a pain. That's going to be by far the most expensive thing in our little code. Okay, this is nothing. This is one equation, and yet this is going to be 80%, 90% of the entire time we spend solving. So we'll solve this. Once we figured out what p is, what p verifies this equation, we'll just take the gradient of it minus, and we'll add it to u star. We'll end up with a velocity field that's divergence-free, that contains both step 1 and step 2. Therefore, the sum of both contains all the terms in Navier-Stokes, and that obeys the continuity equation. And so we'll have a proper solution to the Navier-Stokes equation. Okay? So this is the approach we're going to be using. Let me the name. This is going to be a pressure Poisson equation. Poisson equation is a Laplace equation with non-zero right-hand side. Laplace is the zero right-hand side version of that. So I'm going to summarize this in an algorithmic form. I'll make a few observations, and let me see what else I want to do with this. We'll talk a bit about the solution of that equation. We could spend a week on that equation only. It's a tough equation to deal with. I'll give you one solution for solving this equation. It's not going to be perfect, but it's going to be serviceable. Okay, so let me make a few, no, before I make a few remarks, let me summarize this in a So the resulting algorithm will effectively be 3 steps, not really 2 steps. Call it step 1 and step 2a, 2b. So step 1 is going to be a predictor. Predictor is going to be wrong, but it's u star minus un over delta t. I don't know if I specified that. So when I have typed out PDFs, my vectors and tensors are bold. When I'm doing this on the board, I underline my vectors once, and my second order tensors are underlined twice. I'm French originally. I learned to put an arrow on top, and somehow that I lost this habit. What do you guys do here? Arrow on top. I should have. Anyway. Oh. What am I talking about? Okay, so here we put everything except the pressure. So we're getting now into the specifics of the algorithm. It can be the way you put the right, where in, I should say, when in time you put the right inside is up to you. If you want to have a an implicit scheme, you'll want this right-hand side to be at n+1 or at n+1/2. If you want to have an explicit scheme, you'll want to be at n. We'll talk about that a bit more, but this is not really the point of this exercises for this course. So we'll just say, ideally n+1/2, that would give us second order accuracy. Okay, so this is what I'm talking about here. This guy, I'm going to put n+1/2. n+1/2 would suggest either some sort of an iterative scheme, it would suggest some sort of an implicit scheme, it would suggest something like a Crank-Nicholson, it would suggest some level of complexity. If I just put an n here, this is forward Euler, okay, first order accurate in time. If I put n+1, the right-hand side is in the middle of my time step here. This is second order accurate in time. Oh, and I shouldn't forget to mention. So what we'll do in the actual code, I really wanted to put a Crank-Nicholson in, but I just got lazy. So what I did is I put together a simple Adam-Bashforth. So this is second order accurate, but it is explicit. Okay. So I'll tell you a bit more about that. So that's step one. Step two, there's going to be a corrector. We're going to have first a step 2a, which will be finding the pressure. So find P. How do you find P? Well, we just said what it was. We need to solve the Laplacian of the pressure is equal to 1/delta t times the divergence of the velocity u star that we've just generated in step one. Again, step. And then step 2b is going to be bringing everything together. I have my predicted velocity. I have the pressure that corresponds. I can now project. It's going to be the pressure. And that's going to be taking the following step. There you go. So we'll take the gradient of the pressure we'll have just calculated, and we'll use that to advance ourselves to n+1. The big difference with the compressible code is that we're not supporting acoustic waves anymore. Why is that? Well, because effectively, this tells us that this equation is an elliptic equation. It allows any point in our computational domain to fully influence any other point, no matter how far it is. So the concept of finite acoustic time has disappeared. The acoustic time scale now is essentially 0. Wave speed is infinite. Everything equilibrates according to this purely elliptic equation. Okay, so now that equation gives us no support for acoustic waves. Everything is washed out. The bad news is, if what you're interested in is acoustic pulsing of a flow, if you're interested in the noise generated by a two-phase flow, that's not going to help you much. The good news is you don't have to resolve down to the acoustic time scale. So you're going to be able to take enormous time steps in your calculation, no matter what your acoustic time scale truly is in the flow. Okay? So this is pretty complex. This is a tough equation, but inherently it is not tied to any CFL, to any acoustic CFL in your numerical integration. So I've just said it's elliptic. I said it's the most expensive part of the solver. One thing that you obviously the divergence of the gradient. Well, in the continuous world, yes. We're not dealing with the continuous world, we're dealing with the discrete world. If this property is not true, you don't have a numerical projection algorithm anymore. A projection has to be a projection. A projection needs to be such that if I recompute after that step the divergence here, I need to guarantee that this is exactly 0. And this only happens if that guy is exactly discretely compatible with the divergence of the gradient as I use in my calculations. So you don't have any freedom whatsoever in building that operator. That operator discretely is not up to you how to define it. That operator is numerically necessarily going to be the divergence, that divergence here, that discrete divergence here, convoluted with that gradient here. There's no other choice. Any other approach will not work. So really, this is obvious, but the point here is that this needs to be true in the discrete sense. Discrete divergence needs to be, well, I should say here, the discrete those guys are all discrete. We need to make sure that our discrete Laplacian is the discrete divergence applied to the discrete gradient. If you're not discretely consistent, it won't work. Okay, there's a few additional difficulties. One that is always that is recurring with incompressible flows is boundary condition. So what boundary condition should we use for pressure? Any idea? Sorry? Zero pressure? Ah, there we go. So the general answer is it's if you don't have a compressible code, applying a boundary condition on the pressure, think about what we've just done here. If you're into optimization, what we've just done here is we've basically argued that pressure is the Lagrange multiplier of the divergence-free constraint of the velocity field. We've just redefined essentially what the pressure is as a way of enforcing a constraint. It's not easy to put boundary conditions on the Lagrange multiplier. And here, there's a number of arguments that can be made, but there's really an argument of simplicity that can be made as follows. It is easy for us to have a boundary condition on the velocity. That's conceptually something that makes sense. On the edge of your domain, you'll want an inflow, you'll want an outflow, you'll want a wall. You know what the velocity should be there. Well, if you know what velocity is at n, if you know what those operators do to that velocity and say that this velocity still obeys those boundary conditions, and you still want those boundary conditions to be obeyed by un plus 1, the only way you can guarantee this is if your gradient of pressure, wherever you have a boundary condition on the velocity, is 0. Okay, so wherever you want to enforce something on your velocity, it is very convenient to set this guy to 0. So that's what we'll end up doing. Everywhere around our domain, we'll set dpdx or dpdy, depending on the order, on the orientation of our boundary condition. We'll simply set it to 0. So that's another concern, boundary condition. Explicit P, where n is the normal to our boundary condition surface. I should say dpdn is equal to 0. Okay. Well, this is going to be the normal to the boundary condition surface. And that will allow us to not touch u dot n all around our computational domain. Leaves at our boundaries. So there's a couple of things I want to say with this. An important aspect is that this is not physically correct. If you boxed equation here, this is the only process by which we could arrive to some precise, physically accurate statement regarding the pressure at a boundary of our domain. We're making our life easy here. This is not truly a physical boundary condition. What this is compatibility condition. Projection compatible with our desire to set boundary conditions. There are situations where it's not appropriate to do this, and most good in that this we didn't derive from purely a convenience standpoint, which in general is not the best way of doing science, but we'll allow it. Will allow me to do this. Okay, one more problem, and then we'll switch a quick other. We'll switch to the document I provided to you, so that we talk about the rest of the discretization. The last problem associated with this is the fact that now, if I have a domain where the pressure is obtained from a Poisson equation, and where the entire surrounding is such that such that dpdn is equal to 0, I end up with an interesting property. Take my Poisson equation, volume integrate it. Allow me to call this omega. This thing over delta integral of u star dv. This is just volume integrating my Poisson equation, my pressure Poisson equation. Well, I test easily using, you call that Gauss theorem here? Yes? Okay. So I'm going to call that del omega. Graph dot with the domain ds. And then the same way, the right-hand side, I can do the same thing. My right-hand side, I can transfer the divergence of u into a surface integral over the bounding surface of u dot n ds. So my pressure Poisson equation implies explicitly that that equation has to be true. My compatibility condition is specifically stating that I want this to be 0 everywhere. Right? I said dpdn over all the bounding surfaces, I want it to be 0 for convenience. Well, what you see here is that really physically the only thing that we would need is to enforce the entire integral of this to be 0. We're making our life easier by saying, well, let's actually enforce it pointwise to be 0. So now we're enforcing this entire thing to be 0. And this is from the compatibility condition. That means that my u star velocity has necessarily to conserve mass globally. So I have to make sure that whatever flow coming into my domain at the level of u star of my predicted velocity has to leave somehow. Mass needs to be globally conserved at the star level. So this needs to be 0, which means this needs to be enforced. This is not guaranteed. Well, only if we do not do that manually, what happens is that that equation is not true on the integral sense, and therefore there's simply no solution to my pressure Poisson equation. Okay? So if you put together an incompressible flow solver based on pressure projection method, what you'll find is that most likely if something goes wrong, it will show up in the pressure Poisson equation not converging in one way or another. It's almost a guarantee, because any type of imbalance, any type of problem will lead to the pressure simply not having a solution. So if this boxed equation is not verified, you won't have a solution. Assured manually, or else there is no solution. So we'll have a step in the code where we do that, and I'll point you to this. Okay. I'll say one more thing on this level, and then we'll go to the notes. When I solved this equation, I don't know if you observed that, but the Laplacian operator is not an inversible operator. Okay? That means I cannot compute Laplacian inverse. That means that the only way I can have a solution here is if my right-hand side lies in the image of my Laplacian operator. Okay? Well, guaranteeing that this thing here lies in the image of that operator is exactly what I do when I manually enforce this property. Okay? So this places the right-hand side of my Poisson equation into the image of the Laplacian operator so that I can still inverse this equation even though the operator, the Laplacian operator, is not an inversible operator. This is mathematically the underlying idea behind this. Okay, any questions on this at this level? Can you speak up, please?
We keep a boundary condition of pressure as 0 at outlet. Or 1. P is equal to 1 or bound pressure condition at outlet.
You keep the
Pressure boundary condition at outlet where the flow is going out of the domain. We specify the pressure.
No, so what I'm saying here is with this method, you're not specifying the pressure anywhere. What you're doing is you're specifying the pressure gradient to be 0. At the outlet, at the inlet, at the walls, but you're leaving the pressure be. You're basically not saying anything on the pressure. Okay?
But the question is that we require a Dirichlet boundary condition for this.
Oh, so if you want a directly boundary condition?
Yeah.
Is that what you mean? Oh, yeah, well, so you can work it in if you want. If you want to specify some sort of a suction process, this is something that you can work in, but then you'll have to make sure that your velocity U star is compatible with this. So there's always going to be a requirement that whatever you're trying to enforce on the pressure, anywhere on the boundaries, has to correspond to the corresponding, or has to be compatible with the corresponding mass conservation statement, global mass conservation statement. So you can do that. Other questions?
Explain a bit more about the first difficulty, the discrete.
Yeah, well, maybe I can, yes, in a second, but we'll do that with the full spatially discrete form. So for now, we've only discretized in time. So when I'm telling you the discrete gradient or discrete Laplacian or discrete divergence, it's meaningless because we haven't discretized in space. So let me discretize in space. We'll do that with the next document. And then hopefully it will be more obvious. Okay?
So for a closed domain problem, let's say a classic given cavity type of problem, there is no slip notation on the forwards. So while solving this kind of problem in a staggered tree, we usually take ghost points and put the pressure at the ghost points to be 0. So that, how can we put that pressure to be 0? The gradient, it comes out to be the gradient should be 0, but usually we put the pressure to be 0 on the ghost points.
So if you have a closed problem with walls on the sides, okay, then what's going to automatically happen is that your U star, provided you've implemented your convection and viscous transport appropriately, your U star should be always 0 all along the boundaries, sorry, in the normal direction. So there should be no flow into the boundary. That means that all around the boundary, down here, U star dot n should be 0. So this will be automatically enforced, okay? Which means that as long as you take your pressure gradient to be equally 0 in the normal direction, you need to do nothing on the pressure, nothing else on the pressure. You should be able to simply enforce dPdn all around the side to be 0, and that should always work without doing anything manually in that specific case. All right, so let me, we'll switch to in fact was, so I think I mentioned that this was, this came out of a CFD course that I've taught at Cornell, well, this one pretty recently, in fact, last semester. So we went through a series of methods, but this was the method we looked at in homework number 4. And so I thought, because I typed it up already there, I would just tell you, directly share that with you in this way. So I'm not asking you to do any of what I'm asking here, which is not much. Basically, I'm telling them, I was telling my students, here's the method, implement it in the code, and then do a lid-driven cavity problem and check your results, basically. So, but essentially, what I did is wrote a solver that is fairly close to this. So this is the set of equations we're dealing with. I will need to check whether it's based on the Reynolds number or viscosity in the code. I don't remember. Again, I put that together a few months ago now, so I don't remember whether we have a Reynolds or a mu in the code that you guys have. But this is what we're solving in 2D. Now we're going to talk about the spatial discretization. So the spatial discretization will have one specific subtlety. So I imagine some of you, or maybe the majority of you, know about this already. We're not going to use a collocated grid. So we're not going to put simply our variables all on the same grid. We're going to shift the variables to different locations depending on what they are. So if I give you a normal grid, the pressure is going to live on the cell, on the grid cell. The U velocity is going to live on the X faces of that cell. And the vertical velocity V is going to live on the Y faces of that cell. So effectively, thinking about it from a control volume perspective, the control volume that we're going to use for our pressure projection, and therefore the control volume we're going to use for our mass conservation, will be that control volume. For our U momentum conservation, it will be that shifted control volume that will be centered on the X face of the cell. And our control volume for the V momentum conservation is going to be that shifted control volume centered on the Y face of the cell. So I should say here that this is our mass conservation control volume. Okay? We're going to stick to pure second order accuracy in space for all the operators. Everything is going to be centered. Everything is going to be second order. Okay? We could go beyond. And I'm happy to point you to papers that do that. But in the interest of, of simplicity, we're going to stick to that. You might also be interested in whether we're going to talk about finite difference or finite volumes. My perspective on this is the following. As long as you're looking at a second order accurate implementation, it doesn't matter, it's the same thing. So if you're more comfortable thinking about finite differences, then call it a finite difference code. If you're more comfortable thinking about finite volumes, where we're computing fluxes and then taking the divergence of those fluxes, call it a finite volume code. It doesn't matter. Why does it not matter? Because if I give you the velocity u here, it turns out that the volume averaged velocity over that region here is approximated with second order accuracy by the u velocity at that pointwise location in the middle of the phase here. Okay? And as long as we're discretizing everything with second order accuracy, we can switch from this pointwise perspective to this volume average perspective as much as we want. Okay, so we're going to use this arrangement. Why do we use this arrangement? Because it is extremely practical for us to do this when we want to compute the divergence. And it should be clear from what we've talked about before that the divergence operator is a pretty key operator in our algorithm. So to compute the divergence of the velocity with second order accuracy, everything centered, we're simply going to take the velocity here times the phase area if you want. So if you want to think about it from a finite volume perspective, you're going to take this velocity times this area minus this velocity times this area plus this velocity times this area plus this minus this velocity times this area and divide by the volume of the cell. That's the finite volume perspective. The finite difference perspective is this point, or this u velocity minus this u velocity divided by dx, plus this v velocity minus this v velocity divided by dy. Okay? They're exactly the same. They'll give you the same results. And what this looks like is this. In terms of notation, the index will indicate where the data is located. If I'm giving you a j location, that's going to mean same. There's always subtleties. Here what we're writing is, so we're using this notation because it's practical for us to do that when we write it on paper or when we write it in, in PDFs. So it's convenient to do that. In the code, we can't do that. How do I define a plus 1/2 or minus 1/2? So what we'll do is we'll basically call this I, so u here will be implied to be at the cell phase, even though I will give it index I. V will be implied to be at the cell phase, even though I give it index j. Okay, so I'll need integer indices. P of ij will be there, u of ij will be there, v of ij will be there. Okay, and I'll reiterate that when we look at the code in a second. Okay, so now I can unroll the entire discretization, everything centered. How does that look? Well, we can look at everything term by term. duu over dx, very simple. It's uij times uij minus ui minus 1j times ui minus 1j over dx. Explicit, nothing to do, it's all, it just falls out naturally. duv over dy, same thing, though, and now this time we're looking at the u momentum, so we're on that staggered cell, that cell shifted to the x phase. Now I'm going to need to provide a u momentum flux top and bottom here. Well, those are unnatural locations. Now I'm getting into the cell vertices. So I need to provide a u and a v here, u and a v here, and that gives me the resulting term. In order to get those values, we'll simply interpolate. I'll interpolate between those two u's to get u here, and I'll interpolate between those two v's to get the v here. That's it. We can unroll that some more. This is the viscous term. Nothing particular. Now we need a 3-point stencil because this is a second order derivative. Same thing in V. This is my pressure gradient. Pressure here, the difference between the two gives me dp dx at the face. That's convenient, this is where we need it. And then those define the interpolations of the velocity to bring them to the vertices like I was mentioning before. Okay, so this is going to be the strategy we're going to use in space. Second order, everything, second order centered without any. Say it again? The pressure gradient, no, because so P lives at ij, at I minus 1j. If I just take this minus this divided by dx, that gives me a second order estimate of the pressure right here on the face. So the pressure lives at ij, I minus 1j, but the pressure gradient lives at I minus 1/2 j. Okay? So we differentiate between those two values, or we take the difference between the two values that takes us to the face. Other questions? Okay, so I'll add to this just one thing. Well, no, two things. I'll let you read that. I don't think it's my place here to read through those details during the time we have together. We'll look at the code in a second. What I want to say is go back to the full discretization now. Oh, there was a question regarding what I meant. Okay. There was a question regarding oh, thank you very much. Regarding the discrete consistency of the operators. Okay. So this is our divergence operator. Okay? This is now a discrete divergence operator. I don't remember who was asking about, okay. So this is a discrete divergence operator. Okay? This is what this discretely is. This discrete divergence operator can then be applied on this discrete gradient operator. This is the gradient in x. I didn't write the gradient in y, but it's the same exact thing. If you mix them together, that will give you the only possible compatible way to define the divergence of the gradient, which is the Laplacian. In this specific case, what you'll get is, well, it's very easy. This is one. This is dp dx at I plus 1/2, and that's equal to pi plus 1 minus pi over dx. And right here, dp dx at I minus 1/2, and that's equal to pi minus 1 over dx. And our divergence operator x. Well, how do I combine those two operators together? This ties here the definition of the right above here. Minus pi minus 1 over delta x, the entire thing over delta x. That requires my Laplacian to be pi plus 1 minus 2 pi plus pi minus 1 over delta x squared, which would be the natural second order centered compact Laplacian that you would want to have. Everything works out, it's all good. But if you wanted to use a different divergence operator or different gradient operator, you would need to change the Laplacian accordingly, or else nothing would work. Okay, so we're not going to have to worry about this. Our Laplacian is going to be what you would naturally put in. But what I just showed is that it is indeed the discretely consistent operator that our method requires. Okay. Anything I said I would answer later that I forgot? Okay. So let me. Yeah. Sorry. Go ahead. So let me. Oh, I can. Let me tell you, so the big reference for this is not, so Chorin's method was all fine and good. The full package was first used for the purpose of doing numerical, direct numerical simulation of turbulence by Kim and Moyne back in the 80s. Can I scroll? Wait a bit. So it was used by Kim and Moyne to do direct numerical simulation of turbulent flows over 30 years ago. This is still a method that's actively used. It's a very powerful method that's been very, very successful. And so there's still a lot of DNS codes that are based on this approach. My flow solver, the one I used in my research, or at least one of the flow solvers I use, is based on this method. The original method of Kim and Moyne, so 85, is the following. They recognize the fact that if you, so they use exactly that spatial discretization. They did, however, use a specific temporal discretization. They use an Adam-Bashforth for the convective term, which I wrote here. So basically, they use the current time step and what they remember of the old time step to predict what the n+1/2 convection term will look like. This is second order accurate, but this is explicit. This is subject to a pretty stringent convective CFL condition. And then they use a Crank-Nicholson for the viscous part. So I can tell you two things. So we're not going to, again, this is not a course on the single phase flow numerical methods, but I'll make a few comments. Crank-Nicholson is fantastic because it is semi-implicit. It gives you, it essentially allows you to remove the CFL conditions. And so that's extremely useful for robustness. My research code uses Crank-Nicholson for both the convection and the viscous part, for both. The code that I'm giving you is using Adams-Bashforth for both convection and viscous. So if you wanted to do something that involves a thin boundary layer, well, tough luck. The time step size restriction near the wall will kill you. So at some point, if we wanted to make this better, we would need to put in a Crank-Nicholson solver. The Crank-Nicholson solver requires an extra linear solver and some sub-iterations, and so it makes everything more complicated. Pressure projection I talked about already, so I'll let you read all this. So there's one last topic that we need to talk about, which is how do we solve the pressure Poisson equation? Well, if you solve it well, the code will be fast. If you solve it poorly, the code will be slow to the point that it will be unusable. This is essentially what this is about. I don't know how much, I imagine some of you know already quite a bit about linear solvers and preconditioners and things like that. I imagine some of you don't. So I'm just going to give you a quick high-level discussion of what we could do. The simplest possible thing that we could do would be to do a simple point Jacobi relaxation method in order to find the pressure. So basically, we guess some sort of an initial pressure. We see if it fits in our pressure equation. And we use essentially the wrongness of our pressure equation to figure out the new value of the pressure. And so this is what I'm describing here. We estimate the new pressure from how wrong the equation is. And we do that again and again and again and again and again until convergence. The again and again and again, typically it's going to mean thousands of times. So we're going to have to sweep through our domain, relax towards our solution, and then again for thousands of iterations. This is not usable. You could do, instead of a point Jacobi, you could do a Gauss-Seidel. A Gauss-Seidel would be quite a bit faster. You could do instead a Krylov-based solver. So that could be a conjugate gradient. That would be quite a bit faster. And it would also have the additional property that it has to converge in a finite number of steps. You could combine and do a conjugate gradient solver preconditioned by one of those other methods. Now things would start going pretty fast. Ideally, you could precondition a conjugate gradient solver by what's called a multigrid solver, and that would probably be the best. But it would be also pretty complicated to put together. So what I did is I chose what I thought was a reasonable compromise. This would be the simplest thing to do, but this, we can't simulate anything together with something like this. It's just impossible. So what you have in the code that I'm giving you is a conjugate gradient solver that is preconditioned using either a Gauss-Seidel solver or preconditioned using what's called an incomplete Cholesky factorization. I'll show you where it is. My plan is to not walk you through the process. If you're interested, we can talk more about it. Come talk to me. I can point you to publications, to textbooks that talk about this. There's a lot of stuff to talk about on this, but this is not the point here. Okay? And then this is where I was telling them what to do, but okay. So I think we're pretty much done with this. Now we're going to switch to the code. So is everyone?
I think logging will take some time.
Okay.
But I think we can try to log in.
Okay. Okay. Who has never used Bash or any type of shell environment in Linux and doesn't know how to use command line? Okay. So you should sit strategically next to someone who knows how to make use of this. I haven't used Windows ever. That's not true, but almost. So we're going to do everything, scientific computing style. So we're going to use command line. We're not going to double click on anything. So you can sell the mouse. Okay? All profits go to Professor Day, of course. So let me see. I'll walk you through the code. It would be extremely boring, but I think it's important for me to give you an idea of what's going on. We're not going to be changing lots of it right away. It's going to take a while for things to start really changing. You'll have also to excuse, so it's going to take me a while to really remember what I had planned. I didn't type anything, I just put the code together. So I'll need to make sure that I remember what we were supposed to do. Let me go back a bit And so, except for the 3-4 people who've raised their hand, I'm assuming that everyone else can navigate to the directory where they've untaught everything. They can change directory, move back and forth, do an ls or an ls-l, list the files, and they can open them up in whatever software that they prefer for reading source codes. My preferred software is Emacs, and so that's what I'll be using. Okay, you're free to do whatever you want, doesn't matter to me. Let me tell you about the structure of all this. So hopefully you're, I should probably, okay, I'll do one thing is I'll move that up there. So you should have a compile and run.sh file and an src for source directory. That source directory contains 3 files at this point, all flagged as F90 files. One called demo flow. This is the extremely carefully chosen name for this little toy code that I've put together. One called pressure that contains specifically the pressure solver. And one called visualize that takes care of all the I/O needs. There is not much in that you really need to know about in details for the rest of for the next 2 weeks. But I think the more of that you know, the more comfortable you'll be manipulating the files and doing your own thing with it if it's of any interest. So we'll go through each of them. So visualize is specifically what is going to generate output that can be used in Nsight. We'll test Nsight in a second. Pressure.f90. I extracted here just the pressure solver. What solves the elliptic Poisson equation for the pressure. Demo flow is everything else at this point. It is not the most cleanly written code. It's written with a very clear goal, which is simplicity. So it is not object-oriented. Everything is present in one module at the top, and that module is shared throughout the subroutines that show up later in the code. There's a couple of calls that initialize the variables, and then there's a time integration loop, and then the code returns. Okay, so we'll talk more about the source in a little bit. For now, I would like us to talk a bit about this script called compile and run. This thing is a bash script. If you're not used to bash and you've done other type of shells, that's fine, doesn't matter. It's simple enough. It is not the way you would want to do really scientific computing code management, but what I'm doing here is basically I'm removing all pre-existing trace of a previous run. So I'm removing the existing executable that might be present. The executable that is obtained upon compilation is called demoflow.exe. You see, I still have some remnants of what Windows is. So I'm just removing that. I move to the source directory. I remove the a.out, which is the standard output for the compiled code, any module file that has been generated in the compilation process, and any object file that has been generated in the compilation process. So basically, the first thing I do when you run this compile and run script is that I clean everything up. Everything that's left is the raw source. Then, compile. I have 2 variables here that are defined. One is called debug flag, the other one is called optimize flag, OPT flag. I have here what I just copied and pasted from my compilation scripts that I use for my code. The first one contains standard debug flags that would be used with gfortran. So those are flags that help you identify what went wrong with your execution if something messed up. The OPT flag is the way you would want to compile the code to get the best performance. The most basic thing here is that the optimized compilation is based on has this -03. That's a pretty universal statement that says optimization level 3. Make it as fast as you can. That's something that you tell the compiler. So here we're telling that gfortran. In comparison, the debug flag version doesn't have any optimization, and it has instead a number of things, but the most important one is this dash G that says we're going to debug with this. We're going to try to figure out what's going wrong. This is all that there is to this compilation. I'm calling gfortran with either OPT flag or debug flag, depending on what we're doing. And then I'm putting here the list of the files that need to be compiled, demo flow, pressure, and visualize.f90. What comes out of this is an a.out in the source directory. Whoops. I move this down to the directory where this compile and run thing is located, and I rename this a.out into demoflow.exe. And then I directly, I forgot to tell you, right away, so I guess I'm doing that twice. Right away, I remove all the objects and module files. So this way, you always have a clean compilation directory. Then I move back down to the lower level. So I move back to where this compile and run thing is located. And I just directly run the code. So my assumption is that some of you would be new to actually running your own codes. And the main error that I was making, a number of people were making when you first start in this activity, is that you forget to recompile. You change the source file, and then you run the code again, and you think, well, I just changed it, and yet it's giving me the same results. What's going on? Well, what happened is you forgot to recompile. This avoids this problem altogether. The compilation is short enough that it basically, every time you want to run, everything will be cleaned up, recompiled, and run. All right? Does that make sense to everyone, or are there big questions that require us to spend some more time? OK. Good. So I would suggest that the first thing we do is run this code. This is where everything is going to fall apart. We'll see. I know it's going to run for me. So the idea here is to just execute, compile, and run. It will take this code, compile it, and execute it. I'll do it. I expect that there might be issues. I don't know what those issues might be. So this is where you tell me what went wrong. OK, so the file, so I heard permission denied. You cannot execute the file that's not executable. I imagine that, so my file was executable, but in the process of downloading it, it's not executable anymore. That's something that will have to be done every time. All right, so that's not a big deal, but it is something that needs to be changed. You'll have to do a ch mod user plus execute, okay, ch mod u plus x of the file. Sorry, not of the file, compile and run, okay? So if you have this issue with permission denied for executing, you have to do a chmod u plus x compile and run.sh. Okay? So once you've done that, this little script will now be executable, and things should be hopefully running. So let me know. If there's still problems, let me know. It's running? Okay. Oh, well, so there's another thing. Now that I think about it, the other thing we could do is simply run, instead of every day we'll have a new code, you could just do an sh, yes, an sh. Is it sh? Yeah, so an sh of compile and run will work as well. So this says use your shell in order to execute, compile, and run. That should work equally well. And that doesn't require changing the permission. So you'll be used to that quickly. But you should write down, either you do a chmod u plus x of the file, or you run it by doing an sh of the file. Both should be equally fine. So what you should see is this, hopefully. numbers. So who sees that? I'm very worried that only 2 people are. Okay, 3, 4, all right. 5, 6, 7, 8, 9, 10, 11. We're getting there. So you guys are good. It all runs fine? It all runs fine? Yeah, so Insight will be the next. Okay, so you want to do. Let me show you. Oh, what's going on? Is the keyboard unplugged or something? Oh, oh, so you're in the KSH. Where are we here? Oh, okay. Let me brute force do this. Okay, so what I did here is, so you were in the source directory. You had to be one directory up, which you do by doing, which you can change by doing a cd ... You know this, so you can help him out a bit. The other thing is, you were running a different. So I don't know why, but in fact, this is. Huh. So it was running KSH. So KSH is a different. It's a different shell. Shell is what's used to essentially the application that controls this window, and this is not necessarily the easiest shell to use. In that shell, there's a number of things that don't exist that can be very practical. So if things have worked okay at this point, hopefully they have. You should have done a few thousand steps. 2,500 steps. Let me scroll back up, in fact, to tell you what's been going on here. This is what the code outputs. Very little at this point. The first column is the step numbers. It basically tells you what is the time step, the current time step. The second column is the time, the current time. Then you have the maximum CFL. So basically it tells you how fast the time integration is going in a non-dimensional sense. This is a number that, because we're running explicitly, we want to keep that number well below 1. The code will start becoming unstable because we're running explicit. As soon as this number goes close to 0.5, 0.6, 0.7, 0.8, it depends on the case. It will be case dependent. So we'll keep it reasonably low here. 0.5 works fine. The maximum u velocity in the domain, the maximum v velocity in the domain, the maximum value of the velocity divergence. That should be identically 0, right? We are solving an equation or a set of equations that require a 0 divergence of our velocity field. It is not identically 0, but it's pretty close to 0, 10 to the minus 4. It's good enough for our purpose. We could make this 0. That would lead to a more expensive pressure solver. So this is a trade-off between accuracy and cost. And then the other thing I have here is this p iteration column that tells you how many iterations were done in the iterative pressure solver. This is where we do most of the work in this current single-phase code. This is where we basically crunch this elliptic equation and try to do our best to find the pressure that satisfies it. Okay? I bound it. I'll show you that in a second. right now I'm saying at most do 100 iterations. If this is not enough to get good enough convergence, give up. Why? Because, again, it's a trade-off between cost and accuracy. We could get more accuracy, but we would spend our time waiting for a solution. I don't want that. OK. This thing runs, I think, for a set time. Yeah, it goes to 20 time units. OK? And then it stops. And it should tell you something about the time the solver took. On my laptop, it took 27 seconds. I need to get a quick feel for how quick or fast it was. Can we go around quickly and have a couple of people on each row tell us what their number is? 24? 25? 25? Oh, you win so far. Anyone unreasonably higher than 27? OK, that's a relief. So it seems I'm going to be the slowest, which means if I can do it, no excuse, you can do it. OK, so now the next thing that might break is visualization. So we're going to do an ls-l. This lists the files in the directory. What you should see is the following. We started from compile and run, this magical compile and run everything and clean up after yourself, and obtained, that and the source, the src directory. What you should have now in addition is the demoflow.exe file that is the executable. You should have a fort.60 file. I should have given it a better name. I'm realizing now that I didn't, but I'll tell you what it is in a second. And there should be a viz file. We'll do an ls-l of the viz file of the viz directory. And what you're going to be looking at here is the structure of an Nsight gold format output. I told you we're going to stick to this single output format. We could have done many other things, but in my experience, Nsight is pretty good. And so I'm going to suggest that we use that. What's in the viz directory? There is one file that you can read. It's called demoflow.case. This is the so-called case file. This is what you will open in Nsight, the visualization software. Upon opening that, you'll have access to everything that the code has calculated. We can right now take a look at what's in there. So if we do a more of viz/demoflow.case, this is a very simple ASCII file that tells you everything about what I've been outputting. I'm outputting in a format that is Nsight Gold. So this information I'm telling Nsight. Nsight will parse this. It will contain some geometry information about the computational domain that's going to be contained in the file called geometry. It will contain 3 variables. A vector variable called v. Okay? It will be located in the subdirectory v, and it will have files called v.00001, 2, etc. It will be incrementing in an integer basis. We'll have the pressure. So v is going to be the velocity. P is going to be the pressure. P is a scalar. Okay? So per grid cell, I have a single value. For the vector, I'll have, in fact, 3 values because we're going to be tricking Nsight into thinking that it's a 3D simulation. And then I'm going to be outputting the divergence as well. That's essentially all that there exists in the simple flow solver. There is this little 1 here that is present before the name of the variable. This refers to the type of the time stepping information. The time set is time set number 1. It contains 201 time stamps, starting with first file number 0, incrementing by 1, with all the following time values. This is just text that I'm outputting on the fly as the code runs. Okay? Nsight knows how to read that, and then Nsight knows that from there, it needs to read the geometry, which is information about the mesh, it needs to read then in each of these files, in each of these directories, I should say, the proper timestamp. So I can show you, for example, what v looks like. So viz v, that looks like a whole lot of v.000 dot a number. Okay? Those are all my timestamps. Okay? Let's see if Insight works. So we will simply start. There's an S variable? So, okay. So the fun thing about doing that live like this is that you'll help me debug. So S is a scalar that I had at some point that I thought would be too much for us to talk about. So an additional scalar transport equation that I removed. At least I thought that I removed it. My guess is that, where am I here? This S should be empty. So this is, I just create the directory because I forgot to not create the directory. So there you go. So never mind this. That will give us a nice little thing to try. Fix. Now, I don't know where Insight is installed on your machine. Just type Insight? Okay. Say again, Insight? Insight 102, fantastic. Okay, so same thing for me. I'm not online right now. As a result, I cannot reach my Insight server, my Insight license server. And as a result, when I type Insight, I should have the same situation as you, which is that I don't have a license right now. Yeah, you can say it yourself.
You please write Insight 102 space minus X. X should be in capital. Insight 102 space minus X. Otherwise, your that Insight software would crash.
Oh. Okay. So you have to add the dash X.
X should be in capital.
Oh, so.
Insight 102 space minus X.
So you should, yes. Question? So you should be getting to that screen here. Yes, no? What this should tell you is that there is no license available. We didn't pay for all of you to run Insight. But it gives you the option to use Insight free, so a free version. Sorry?
Can I log in your system using my?
You can, but I don't. That's fine for me. This is all good. This way I do the same thing as them. Okay, who is not able to start Insight? So logically, that means everyone is able to start Insight. Awesome. So we'll click on the third choice, which is Insight free. And it should bring you to this welcome to Insight free screen. What we're going to do is click open other file. Okay. And it should open something that looks like that. Mine is running on the Mac, so it might look, the windows might look different. But essentially, it should show you the directory in which you started an site. And we're going to be able to double click the viz directory. And the file we're going to want to open is demoflow.case. Okay, so we'll do that right now. I realize that you probably cannot read that, but this is the viz directory. I'm going to double click. I did promise that you wouldn't double click ever, but that's, I guess I lied. And then there's this demoflow.case file, the text file that we talked about a little bit. You're going to select this thing and say OK. And you should have a beautiful red rectangle. So it seems, so any major issue here? Okay, so in the interest of time, let me know, what is the situation? Who is not able to get to this beautiful red rectangle? Okay, one person here, 2, 3, 4, 5, okay, 6.
So I guess there is some problem because I have logged in different systems, that's why it will be fine, I guess.
Intel do flush locked fail. So you logged, yeah, I don't know if that could have.
Multiple, that's why might be, I'm not able to. Okay, चलता है पर मेरा नहीं चलता, थोड़ा दिक्कत हो रहा है.
Oh, I can do that later. So you didn't have the dash X though, right?
This will, I will start.
Okay, and then free. Yeah, okay. Who else? So if things are not work, if did you put the dash capital X?
102. First do a control C and then.
Yeah, you'll have, yeah, this capital X. Oh, good. Who else? Any other issues? Okay. I see lots of beautiful rectangles, so we're good to go. So I should have said something about, so there's, I'm realizing now that things might be slower, at least at first, than what I was hoping. So there are three things I'd like to do. I'd like to actually show you the code and what's in there. And then I had planned 2 cases for us to run. And this is the first one. This is, as the name of the directory in which you're running indicates, probably, this is a Poiseuille flow. And don't tell me this is not pronounced the right way. I'm French, I know this is Poiseuille. So this is a simple channel flow, laminar 2D. We're starting from a plug flow. So uniform velocity at 1 here on the left, a wall here, and an outflow here. And this is a simple verification exercise. The point here was to verify that we get as close as possible to an exact Poiseuille flow profile at the exit. Okay. The second case I have is a Stroll number calculation. So I build this little cylinder and I'm flowing past it, and depending on the Reynolds number, this thing will start generating von Karman vortex streets. Okay, so we'll have a series of separating vortices from the cylinder, and the frequency at which the vortices shed is something that has been studied for decades, if not more. And so that's something that I wanted us to check also using this code, okay, to make sure that things are not completely bogus. So we'll do that reasonably quickly, but I do want to show you inside the code. So I want to walk you through what's going on there so that you're not completely lost. So things are working fine. We'll go back to that later. I'd like you now to open with your favorite text editor the demoflow.f90 file. Okay? So you should get to something like that. Maybe not quite as nice, but reasonably close. We're there? You have the code open. So the main driver for the code is this demoflow.f90 file. I was lazy. There's no encapsulation, there's no object-oriented approach, there's nothing. There's a module that contains everything, and that module is shared with all the routines. Okay, so this way everything is available everywhere. Data is basically global. This is the simplest way that you can write a code. If you don't want to think about computer science, but you just want to actually do the science with the computer, this is a reasonable way of doing that. So I'll walk you through what's going on there. There's a lot of comments, so if you don't know what to do tonight, you can read those comments and think, oh yeah, I understand. But I'll walk you through those things. The first two integers here that I'm defining are defined as parameter. That means that they're going to be constant. They're going to be replaced at compilation time by the actual value. They're not going to be stored as a variable. This way everything is faster. There's two of them. There's WP and SP. SP stands for single precision. WP stands for working precision. Effectively, what I'm saying is I want my real numbers to be single precision, meaning encoded on 4 bytes for visualization. That means that I will have essentially 10 to minus 8 precision with my visualization data. But I want my calculations to be done with a precision that allows me to go down to 10 to minus 16. Okay, double precision, 8-byte integer. 8-byte reals. Then with this in mind, I'm going to be defining every single real as a working precision real. And so that's how it looks. Every time I write a real, it's going to be written as the value underscore WP. That means this is a working precision, double precision variable. Okay? This is a habit that you can develop. Once you have it, it's easy to do. Until you develop it, you'll forget, and that's fine. I have a first chunk of parameters that I expect you to modify. Regarding the time integration, basically simple things like what is the maximum time step size, what is the maximum CFL, so what is the rate of integration of my equations that I'm willing to accept. And I'll tell you a bit why I'm specifying both. And basically I'll tell you right now, the code is adjusting. If the CFL goes up too much, the code will automatically reduce the time step size. Okay? It's because I'm running explicitly, it's pretty much a required thing. This time tells when you want to output an n-site file. I don't output every time step, or else we would fill the hard drives very quickly. So that says the typical integration time, so the size of the time step, and this says when do we dump a file to look at in n-site. So here you can see there's a factor of 10 between the two. That means that every 10 steps taken by the code, we dump a file. That says when we stop integrating. Max time, once we reach 20 time units, we stop. Alternatively, once we reach 5,000 steps, we stop. The first one that's true will stop the code. We need to solve the elliptic pressure Poisson equation. As I mentioned, that this is an expensive exercise. I'm specifying 3 ways that we decide that we're done at each step with the solution of a pressure Poisson equation. Either we've reached 100 pressure iterations, and then we say, well, all right, I give up, I've spent already too much time. Or we've reached a convergence, either relative or absolute, of 10 to minus 4. So basically, once I've gotten down the error in my equation, in my Poisson equation, by 4 orders of magnitudes, I basically say, okay, it's probably good enough. We could make this more stringent. What would happen is the cost would shoot up. I have some information about the mesh size. This is a long channel. As a result, I have a 400 by 42 cell mesh. 400 in X, in which the flow is taking place. 42 in Y. Why 42? It's kind of strange. Well, it's really 40, but then I'll tell you how I'm dealing with walls. I basically have 40 cells in my channel, and then I have one cell at the bottom that serves as a wall, and one cell at the top that serves as a wall. Okay? This is my domain size. Lx is the length in X. It is 10 units, whatever, it's non-dimensional. Ly is 1.05. Why 1.05? Well, it's really 1, but again, I've accounted for a little cell at the top and at the bottom. That gives me exactly a height in between the walls of 1. I have a kinematic viscosity that's specified here. I'm calling that K nu. Okay, so I don't have a Reynolds, I have a viscosity. That viscosity is of 0.01. From that, we can, knowing what the height of the domain is, 1, what the velocity is, we'll see it's 1, and what this K nu is here, which is 0.01, we can find a Reynolds number for the channel to be 100. That should be well into the laminar regime. We expect a Poisson flow, therefore we're good with 2D flow solver. I'm allowing for gravity, but we don't need that here. Then here comes a lot of the more detailed stuff. One thing, the code is assuming, yes. Why am I using what? Because I don't want to have to rewrite my code if I want to switch to working precision. So basically, I want to be able to go to quadruple precision or to single precision. I want to be able to dynamically change the precision at which the calculations are done without having to rewrite the entire code. And the way you do that is by making the working precision, the way the real variables are defined, as a parameter in your code. If I want to run much faster, I can just run everything single precision. And to do that, I just have to say that WP is equal to 4. The calculations will be less accurate, but everything will be quicker. If I want to run more accurately and slower, I can put everything to 16, and now I'm running quadruple precision. I can resolve much smaller numbers, and I can look at much wider range of variations of parameters. Okay, so this is precision of calculation. Well, we'll talk about that when we look at the pressure depth 90 file. So I'll mention that again soon. Okay. X is my mesh in X. Y is my mesh in Y. X and Y are the locations of the cell faces. So a cell ij, will start with a face at location x sub I and end at location x sub I plus 1. It will be bounded at the bottom by location y sub j, and at the top by location y sub j plus 1. Okay? The location of the centroid of the cell will be stored at location xm sub I for x middle, and ym sub j will be the height of the centroid of the cell, y middle. I'm storing my mesh size, the cell width, as d, a single number, because I'm assuming that the mesh is square. This is another simplification that's not particularly required, but that allows us to not worry about lots of things. So basically, I'm assuming that dx and dy is the same, I'm calling that d, and that's all we're going to be using. I have this variable here that's very important. It's called mask. That tells me whether my cell is a wall or a fluid. If mask is equal to 0, the cell, so if mask of ij is equal to 0, then cell ij contains fluid. If mask of ij is equal to 1, then that cell contains wall, a solid. I'm not going to be computing. This is how I'm going to enforce some of my wall boundary conditions. That's how I'm going to be able to put a little cylinder in the middle and things like that. Okay, my solution vector, u velocity, the v velocity, and the p pressure. Okay? And then I have lots of additional things. Well, not an enormous number, in fact. I have this h sub u1, h sub u2, hv1, hv2. Those are the residuals that I'm going to be using for the u and the v equations at time n and n minus 1 that I'm going to be using as part of my Adam-Bashforth time integration. I need a place to store the residual of my equations. This is the same notation as in the document that that we talked about a little bit before, where I had h's there. Div is the divergence of the velocity. Then I have my current time, my current CFL, my current time step size, my old time step size, the number of time step I've done, number of pressure iterations I've done. I have pi down there. That's an easy one. So this is pi. I have a place where I'm storing my Adam-Bashforth coefficient, which is basically for uniform time step. This is a linear extrapolation from time n minus 1 and time n towards n plus 1/2. We'll have more opportunities to talk about that. So we'll see that soon. And then I have those three things here: P-lap, U-lap, V-lap. So if I'm assuming constant density, my right-hand side, as well as constant viscosity, my right-hand side of the Stokes equation can be rewritten as being essentially one over Reynolds of Laplacian of U and Laplacian of V. Those are those Laplacian operators. I'm pre-storing them because it's going to make my life easier. And this is my pressure Laplacian operator. So those arrays will contain divergence of gradient of anything. And I'll show you how we use that later. Some additional complexities. How big the arrays are. Well, the domain starts with cell 1 and ends at cell nx in x. It starts with cell 1 and ends at cell ny and y. But we need additional storage in order to avoid putting if statements everywhere. And so this is why some of those arrays start from 0 and go up to nx plus 1. Some of those arrays some of those will even start later. There's a number of different things here that have to be thought about regarding the size of the arrays to make sure that we avoid all the extra unnecessary if statements once we reach the edge of the domain. This is getting into the details of the code. I don't want to spend too much time on that. It's going to become extremely boring, extremely fast. We'll have more opportunities to discuss those things. Okay, the main thing that I'd like to show you is the main code driver. So the main place where we initialize, run the time integration, and finish the execution. This is where I run the code. This is program main. This is really where we get into the code. I start off by checking the current time. I set up, so I do this call demo flow setup. I initialize the mesh, the wall, and the various boundary conditions. And we'll look at that in a second, and I'll ask you to modify those things. Then we initialize a whole lot of different things. So those Laplacian operators, for example, we initialize all that. We say that we start at time 0. We initialize our time step size with the maximum one that we thought we would be, that we expect that we'll be using. We initialize our visualization. This is where I create my directories, in particular this S directory that shouldn't be there. And then this is the time loop. The time loop simply repeats until the time has reached the maximum time, and I guess it's an N, not an OR. Oh no, yeah, that's what I meant. So we stop either when we reach the maximum time or the maximum number of time steps. When the first condition is reached, we just stop the execution. The first thing we do is we compute what the next time step size, the next delta t should be, based on the CFL. If our CFL is too high, we'll reduce the time step size in accordance. This allows us to get still a reasonable performance from an explicit code. Okay? We increment our time counter. We output, so what I showed you before, the step, the time, the maximum CFL, maximum velocity, all this is where I output all this. Then we'll solve this thing here, this velocity step. This is step 1 of Chorin's method. This ignores the pressure altogether. This just advances the Navier-Stokes equation without pressure. What we get out of that is U star. U star is not divergence free, we're not done. And then the second step is here. This is the pressure correction. Pressure step will solve the pressure equation, apply the pressure correction. Okay, so 2A, 2B, this is all going to be done in there. And then I dump the visualization information. So if the time is right, I just dump my velocity, my pressure, so that you can then visualize it. And that's it. That's the end of my loop. Then I get the current time again, look at the difference, and I put that as well so that you know how long it's taken to run the code. And then this is something I'm doing specifically here because we're looking at this Poiseuille flow problem. I'm just directly outputting the profile at the end because I want to check that this profile indeed looks like what it should, and what it should be a perfect parabola. Okay? Any questions on this main code here? It's simple enough, right? Just a simple set of initialization, the time integrator, and then some very basic output. So now obviously there's a lot in there. So I'm not going to go into a whole lot of details here. We'll have more opportunities as time goes by. I'll point out that in the demo flow setup, I highlighted here that this is something that you want to modify that. If you want to run a different configuration, this is where you have to go. This is why I create the mesh. So basically, I'm assuming a uniform mesh. So for the most part here, you can change the mesh size. So the domain length, the number of cells, and where this thing is located. For example, here, my first X face is going to be located at 0, and the last one will be located at LX. Okay? If you can read this loop, this is a simple do loop that will uniformly spread points between, or spread cell faces between 0 and LX. With J, same thing. Going from 0 to LY, except then I'm shifting by half of LY, which means I'm actually going from minus LY over 2, sorry, to plus LY over 2. So I'm centering my channel on 0. From this, I can compute the cell centers by just averaging the cell face locations. I'm going to create walls here. I'm saying everything is fluid except the bottom layer and the top layer. This is going to be walls. I'm specifying an initial condition where the entire U velocity is 1. No V, no W velocity. Sorry, no V, no, and pressure. In this case, doesn't matter. The pressure will be solved on the fly. I'm saying here, so I guess this is a remnant. I had periodic conditions, but this involved a lot of if statements, so I removed that. So it doesn't really matter. The inflow condition here is basically a statement that I want to impose a Dirichlet condition on the x minus side of the domain. So on the left of the domain, I will impose a constant velocity at 1. So I'm going to be flowing at 1 and the left, top and bottom wall, starting initially with 1 everywhere. If my code has been properly implemented, we should develop boundary layers and establish a Poiseuille flow reasonably quickly. This is going to be ugly. So demo flow init is where I'm putting together all the operators. So I'm just going to say, you know, it's what it is. We can't make this a trivial thing. There has to be some non-trivial aspects, and that's one of them. We'll need later random number generator. I'm seeding it here. So I'm making sure that we don't get always the same random numbers. I'm applying Neumann condition on the masks. So I'm assuming that the mask you've specified inside apply also on the edge of the domain. I'm generating the mesh size, this D variable we were talking about. I'm making sure that D is the same whether I compute it in X or in Y, If it's not, you don't have a square mesh, I return with an error. Say it again? The random seeding is because we're not going to use random numbers here, but tomorrow we'll start playing with particles. And I'll want to have the opportunity of putting a random position for my particles. So I will very soon want a random number generator. If you don't seed your random number generator, it will always give you the same numbers. Okay, so the seeding process is a process by which, there is, generating a random number is an incredibly challenging exercise. The way we're doing this, having some number based, in fact, I think, that allows us to have something that's close enough to being truly random. I'm creating the pressure Laplacian. Reasonably obvious what this is, I hope. At position I, at position J, in the direction X, so the first dimension of my problem, I have 3 stencil coefficients. One sitting at my location, no shift. One sitting at -1 to the left. One sitting at +1 to the right. The one that I apply to myself is -2 over d squared. So -2 over delta x squared. That's the diagonal of a 1D Laplacian operator. The upper diagonal, the lower diagonal and the upper diagonal are +1 over dx squared. This is just -1 over dx squared, +1 over dx squared, -2 over dx squared, +1 over dx squared. This is a simple 1D Laplacian operator that I'm storing in the form of an operator. I'm storing the actual diagonals here. Same thing in Y. Okay? We'll talk more about that, and if you have questions, come talk to me. Why am I doing that? Well, because I want to put walls. And every time I put a wall, I need to enforce a boundary condition. Specifically, I want to enforce that dpdn is equal to 0. Okay? And I do this, well, down here, in fact. What I'm doing is every time I find a wall on my cell to the right, so if at I+1 I have a wall, then I need to modify my pressure Laplacian to account for the fact that dpdn is really equal to 0. So this is what this does. It is basically uploading, handling a priori all the ugliness of boundary conditions. It allows me to create modified operators that contain the information of where the walls are, so that I never have to do if statements later as we continue the calculations. So again, we can talk more about that later. If you're interested, you are welcome to treat it as a black box. It is reasonably readable. It is not too much there. So I'm doing that for the pressure. I'm doing that for the Laplacian used for the u velocity, and then for the Laplacian used for the v velocity. And then we're essentially done. That's it. This is the initialization. I have now 2 more things going on. Well, no, that's not true. 3 more things going on. I need to do the predictor step of Chorin's method. I need to do the corrector step, and I need to show you how I visualize. Okay? So the predictor step is right here. This is this little chunk here. If I can zoom in. Okay, good enough. This is a loop over the entire domain where I compute everything that I listed in the notes that we looked at a little bit before. So I'm basically saying this is the U momentum equation residual. This is the convective term, and this is the viscous term. And that's it. This is how this is the right hand side of my first predictor step. Same thing for the V equation down there. Once I've created that, I do the Adam-Bashforth here. What is Adam-Bashforth? If you forget about the Adam-Bashforth coefficient, basically upwind forward Euler would be saying U is my old U plus the right hand side that I've just calculated times dt. That's it. That's essentially all that this would be if we were doing first order time integration. We're doing second order, so I'm using the operator. I'm using the right-hand side I've computed at that time, but I'm also remembering the one I had at the previous time. I need to put some boundary conditions, make sure things don't start flowing inside the walls. This is where things become a little bit tedious. So I'm not going to bug you with this. You're welcome to read that. This is where I make sure that nothing messed up occurs in the wall. This was the predictor. Then we need the corrector. The corrector will need two things. We'll need to compute the divergence of the velocity. We'll need to make sure that our velocity obeys global mass conservation. I mentioned that. If we don't do that, we don't have a solution to our pressure equation. So this is the first thing we do. We enforce global conservation. What do? I'm assuming that the entire flow will be going from left to right. I'm simplifying my life. Essentially what I'm saying is I need to surface integrate the flow coming from the left, surface integrate the flow coming out of the right of the domain, and if there's a mismatch, I'm going to adjust the right boundary. I'm going to say that I basically need to make sure that I flow out everything I've flown in. This is what this does. I do the left flow rate, the right flow rate, and then I correct to account for the difference. Once I've done that, I'm happy enough with this. I can compute the divergence. The divergence, once divided by dt, is the right-hand side of my pressure Poisson equation. This is my divergence. Ui plus 1 minus ui, vj plus 1 minus vj, all this divided by d. That's it. Then I solve my pressure. I'll show you that in a second. And then I correct the velocity. How do I correct the velocity? Well, this is step 2b. I just add the pressure gradient. This is what this looks like. Pressure gradient in x applied to update u. Pressure gradient in y applied to update v. And that's it. Just to make sure at the end I recalculate the divergence. This should have decreased significantly at the end, and then I output it. I know I'm rushing through that. Hopefully this is still giving you a reasonable idea what's going on. The last thing in this file is the adjustment of the time step size. This is this last routine called time adjust. What this does is it gets the current max CFL. It looks at the 1D U CFL, a 1D V CFL, and the viscous CFL. It takes the max over the entire domain, and it compares to what I specified at the very top of the file. If it's larger than what I specified, I just reduce my time step size right here. Yeah, right here. Okay? So this reduces the time step size, that's it. It can also increase it if you're running too slow. Okay, so this was the first file. There's two more, but they're very, very specific. I'd like you to open pressure.f90. Okay. Control X. Okay, is it readable? I'm not sure what the size was before. In the back, you can see. Okay, so this is purely a linear solver for the elliptic Poisson equation. We could talk for weeks about that. We're not going to do that. What this is a pretty much self-contained conjugate gradient preconditioned by either a Gauss-Seidel relaxation or an incomplete Cholesky factorization. If those words mean nothing to you, don't worry about it. It's not going to matter much. We're not going to touch this. Well, we're mostly not going to touch this. If you know how Gauss-Seidel works, we need the diagonal. If you know how an incomplete Cholesky works, you need to modify the diagonal in some way. This is what's done here. I compute an initial pressure residual. I call my preconditioner, and then this is where the conjugate gradient is. So if you've been exposed to conjugate gradients, you should look at that and think, oh yeah, I recognize this. I'm not going to go through the details. The idea is that we have this pressure loop until we've reached, so this is where there was a question regarding what were the parameters that we discussed about the pressure. Well, there's 3 of them. I'm saying that I'm going to exit if any one of the 3 conditions, the following 3 conditions are met. Either I've iterated what I consider to be enough, meaning that the cost is becoming too large and now I have more than the specified number of iterations done. Then I'll leave. Or my residual, which is contained here, is less than the specified value. That means that the error making with my equation is less than the specified value in an absolute sense or in a relative sense. If either one of those 3 conditions is met, we just exit. This involves full domain operations done many times through that pressure loop. So this is going to be many times more expensive than the predictor step. The predictor step sweeps through everything a couple of times and is done. A couple of times, again, meaning once for U, once for V. This will sweep through the entire domain hundreds of times. So this is going to be pretty much the entire cost of the solver. And this is my preconditioner, and that's it. So I'm not going to go more into details here. I will now open the last file, which is visualize. Okay. This is, there's no science here. This is only knowing how to output, doing I/O. This is nothing exciting. The first time around, I do this thing here where I create the directories. This is my bug. I need to get rid of that. I don't need to create this S directory. Then I create the geometry of the problem. This is specific to the Nsight gold format. I'm not going to bug you with that. Essentially, I'm telling you what the X and Y's are. If you want to read through that, if you have questions, I'm happy to tell you about it. I tell Nsight which cells are fluids, which cells are wall. And I create an initial case file that contains essentially no data, just the mesh. And then that's it. The main thing is this visualize underscore dump. This checks whether it is time or not to dump the data. If it is, then it goes through the process. It will dump the velocity data. It will dump the pressure data. It will dump the divergence data. And then it will update the so-called case file to say, hey, by the way, I've added this, this timestamp information. And then that's it. It completes here. So that's it. We've looked at the entire code. Thank you for being patient with me, because I realized that this is boring reading through, source files. But this is, I think, one of the simplest, pretty much almost truly scientific computing code that I could think of, at least. It is not very long. It is reasonably digestible. In fact, I can tell you WC-L of source star.f90. It is 831 lines total. You've seen probably a third of those lines are comments. So maybe not a third, but a fifth of those lines are comments. So if you want to use that as a starting point, feel free. And if you want to talk, read through some of those things and want to talk to me about that, I'm happy to do that as well. Okay. In the next 8 minutes, we're supposed to run 2 flow problems. I think we can do this. But what's going to happen is we're not going to go through the very details of how the problems are set up. We're just going to take a look at the Poiseuille flow, and then we'll take a look at the Stroll number calculation quickly. So you should still have Nsight open with this. My assumption is that you don't know how to use Nsight. So I'll walk you through some aspects of it. If you click on this geometry, complete geometry on the top left, we're going to be able to create a cut through this. The cut is very nicely illustrated here by the scissors. We're going to click on this. That should open up a new little window like this that allows you to specify that type of cut that you want to do. I realize it might be a bit small for you to see. But we're going to be doing that day after day, so I think if things don't necessarily make sense right now, hopefully this will become easier later. So right now we've selected an XYZ cut. We'll do a cut at constant Z. So we'll do mesh slice in the Z direction, because everything I've set up here is in X and Y. Okay? So we'll do a cut in Z, and now we're simply going to take our domain, and we'll have a plane through it, and that should show up as simply a white middle to our red rectangle. We're going to close this window. We should be done with this now. Yes, so you're going to select the complete geometry, go to cut, this little scissor thing at the top. There should be a pair of scissors and one of the top icons. Okay, and then towards the bottom of this window, we need to choose the orientation of the mesh slice. We're going to do it in Z. By default, it should be in X. So you do it in Z, and then you do create, and you will get this, this white region. Okay? So I can show you a few things, but again, we're not going to have time to do this if we want to stick to our schedule. With the mouth, I don't know exactly how. It depends on the configuration of the machine. You should be able to zoom in and rotate. You can zoom in, translate, rotate. I'll let you figure out how to do that. That might involve right click, left click, the middle mouse button, or the wheel if there's a wheel on your on this. What I'll show you right here is simply the fact that you can see the mesh. So if you click on the little sun on the bottom left, it removes the filling of the cells. And what you can see here is your actual grid. The grid that we've used is 400 by 40 grid. Okay, this little sun down there. So we're actually looking at our computational mesh here. Then what we'll do is we'll add some colors, because CFD stands for colorful fluid dynamics. We will click on the clip plane here, which should have now appeared below complete geometry. So you click once on it, you have it selected, and then we're going to go to this little color wheel here to choose how we're going to be coloring that. And we're going to choose which variable to color it by. Okay? Everyone sees the little color wheel that shows up once you've selected click plane. We're going to click on that. And that makes this menu show up where you can select what variable to color with. And here what we're going to do is the simplest possible thing. We're going to click on V, the velocity. We're not going to play around with that. You're welcome to do that more. I don't know if you have a laptop. You can probably do that on your laptop, or else we'll play more with that tomorrow. But we'll click V. By default, V is a vector. As such, it contains multiple components. What you see here is the magnitude of that vector. Okay? So you should all have now the velocity field. I'm going to close this, and now we went through the trouble of telling Nsight about the timestamps associated with the files. The good thing is we directly get the capability of playing this back as a movie now. So on the very top left, you should have this pretty clear those pretty clear icons. If you click play, you should be playing back the calculation that you just did. It's a pretty boring calculation. There's some stuff happening initially, but then we converge reasonably quickly. So let me go back. This is our initial solution. Everything is at velocity 1 constant. Remember, that's what we set up. And then as you run, the boundary layers develop. And you go from your bulk flow to your Poiseuille flow further downstream. Okay, no surprise here. That's behaving the way it should be behaving. The exciting part is that you get to see that dynamically evolving as we read the time. Okay? Everyone able to see that? Or I should say, who's not able to see that? Okay. My plan for this was fairly simple, but some of that we can do offline. You know, I don't know if I'm expected to give you homework for tonight, but if I'm allowed to, go look at how the mesh is set up and how we specify the flow at the inflow, and then go take a look at the fort.60 file that was generated, which is just a profile down there. And you'll see that it exactly matches with the analytical Poiseuille solution. By exactly, I shouldn't say exactly. This is a numerical approximation. It is not exact, but it is extremely close. OK. I want to show you the second case quickly. And I'll let you take a look at what's been changed between the first case and the second case. Really only the mask has been changed a bit, the size of the domain has been changed a bit, but everything else is essentially the same. So I will close this. Well, I didn't need to close it, but I guess I did, so that's it. We're going to move to the directory called 2_Stroll. Okay? My plan here was to have you check whether the Stroll number predicted for the von-Karman vortex street by this little code matches with experiments. You're welcome to do that. And in this directory, there's some experimental data that I've included. But in the interest of time, we'll just run and look at the flow, and you'll see the von-Karman vortex street. Okay? And I'll let you offline take a look at how I've modified the inflow, the initial condition, and the mask creation in order to achieve this flow. And in fact, we'll be looking at this flow again tomorrow, so we'll have other opportunities. So we're moving down from 1_Poiseuille, and we're moving now to 2_Stroll. Okay? It should look like this. There's a PNG file, an image file that shows the experimental data that's available on the Stroll as a function of Round's number for the von-Karman vortex street. I'm assuming everyone knows here what the von-Karman vortex street is. It's fine, right? It's just the oscillating vortices behind a cylinder. The code structure is exactly the same. I've changed the number of cells, the domain size, the centering of the domain. I think I've centered it on the cylinder. I've changed the mask to carve out a little stair-stepped cylindrical region. So we're going to run this the same way as before. Remember, your compile and run.sh is probably not executable. So you should make it executable with chmod, or alternatively, you can just run it like this. What is going on? You could run it as an sh of compile and run. But the idea is you should be able to run this. And it should look like this. Should look exactly the same way as before. The code should be a bit slow because now we have, instead of having essentially a steady flow, you can see that because we have oscillating vortices, the flow is unsteady. It is more difficult to converge the pressure solver. I'm always doing 100 steps. I don't remember how long this was supposed to run, but I think on the order of, I don't know, a minute or so. Okay, so it's done already there?
It's more than 200 seconds.
2 minutes and
200 seconds.
oh, 200 seconds. Okay, so it should be a couple of minutes. Oh, should be 3 minutes or so. And the good thing is also we can visualize this as we're running. So in fact, we'll do that. So while this is running, I will start inside again. Inside free. And I will open the demo flow.case, and I'll do exactly the same thing as before. Except, so now this time you can see the little cylinder that we've carved out. Okay? So I'll create a cut through this the same way as before. So I'll select the geometry, go to the little scissors. I will create a cut in Z. That looks like this. And then I will color this with the velocity. And there you go. So this is still computing, but you can see what you would expect to see at this point. I'll show you just for a second, and then I'll let you go. It's very easy to take to compute the vorticity, for example. So if I go to the little calculator on top here, the second icon, I can scroll down and find Vort. I can specify that I want Vort to act on the velocity field V, ask for it to be evaluated, close that, and then recolor using vorticity. So I'm realizing I'm going very fast. But this is what you get. There you go. So this is your classical Funcom and Vortex treat. My plan, and maybe we'll do that if we still need to warm up a bit on this code tomorrow, which I expect we will need to do. My plan was to have you vary the Reynolds number and see whether the Stroll number responds in a way that is compatible with what you would expect. In fact, the Stroll number is supposed to increase with the Reynolds number and then plateau as the Reynolds number is large enough. I don't remember what Reynolds number this is, but it should be higher than 40 to start seeing some flapping. This might be 50 or 100 or something like this. Okay, so we're, I think, pretty much at the end of our time. I apologize for, it's been a bit rushed, but we'll build up on this. So, we'll see the same code tomorrow and start putting particles in it. So hopefully things will, and also we had a number of kinks to work out, so I think things can work reasonably well in the next few days. Okay, if you have feedback or concerns, come talk to me. We can, or Professor Day as well. We can try to work this out. And in the meantime, thank you for your patience and for your attention. And I'll see you tomorrow morning.